Uh, These are, of course, as well. And one more quick announcement. We know that some people need to go to the next meeting at 3:30, so we will have a short break so that everyone who needs to leave can leave. But we also have the room for longer for anyone who wants to continue discussion and questions afterwards. So, and now I'm very happy to welcome Jessica Young here with us. So Jessica did her PhD in Berkeley as a biostatistician with Nick Jewell, and then worked as a postdoc with Miguel Hernan. And she is now associate professor, and it's always complicated with all the affiliations, at Harvard Medical School and also at the Harvard Pilgrim Institute for Healthcare. And we all know her from especially her work on the G-computation formula and the implementation and generalizations, all the great work. And of course, recently also a lot of work on time to event, causal inference with time to event data and these settings. And so this connects to a lot of the things we are doing here, and we are very happy to have you. Over to you.
Thank you. And thank you so much for this, for the invitation, and thanks for coming, and Conrad and Lisa. This has been a really fun trip. So I'm going to be talking about something called story-led causal inference. But before we talk about that, can
Yes.
they hear me? Before we get into what that is, let's just establish a meaning of causal inference, because this can mean a lot of things to different people. So here, what we mean is a statistical inference that engages with some formal causal philosophy. So things like, how do we define a notion of a causal question, causal effect? How do we reason from that choice of question down to a statistic? In other words, a particular approach to analyzing data. So this requires some kind of causal reasoning process in some way overlaid on top of a statistical reasoning process. So that said, a reading of the modern causal inference literature, particularly as it relates to epidemiology and public health and medicine, which is where I sit and where all of you sit, would suggest to sort of a new reader that there are only two philosophies, basically, from which to approach causal inference with real-world data, and these are very disparate, contradictory philosophies. So I'm going to just loosely call one of the philosophies an interventionist philosophy. People feel very emotional about this term. What I mean by it, and I'm going to call it interventionist. What I mean by it is the perspective that the only acceptable notions of causal effects are those which could be answered from a randomized trial. And the so-called target trial emulation framework, which I know at least some of you are familiar with, is a direct offshoot of this philosophy. And one key aspect of this target trial pedagogy is that it states that the first step of causal inference is articulating the protocol of the target trial, which at least in the first paper that really sort of moved this thought process forward, this Hernan and Robbins 2016 paper, they defined a target trial as a trial you would run to answer your causal question. So the other sort of alternative philosophy that we would come away with is what I'm just, by extension, I'm going to call a non-interventionist philosophy. And I've had people who ascribe to this philosophy very much dislike this term, so I continue to put it in quotes. But basically what I mean is what the philosophy that's reflected on this slide more formally, the philosophy that there is no such restriction placed, that it is not a requirement for causal inference to be grounded in an effect that could be answered from a trial that we could plausibly conduct. More formally, this permits any effect that could be identified under Pearl's so-called NPSEMIE model, a type of counterfactual causal model, which can be implicitly represented by a causal-directed acyclic graph, or DAG. So if you've never heard of an NPSEMIE, don't worry about it. The real takeaway here is that this model permits considering and reasoning down to statistics any effect that the grounding in any effect the interventionist would accept, but more effects. And most notably, the cross-world effect. So the canonical example of a cross-world effect that has created a lot of controversy across these two perspectives are so-called natural, direct, and indirect effects, which would allow thinking about or grounding data analysis in a counterfactual outcome that considers a scenario where an individual receives, say, an active treatment, and then also the value of a subsequent mediator that they would have received under placebo. So this could be classified as a sort of metaphysical quantity in the sense that it could never be directly observed. But the other type of effect that has raised a lot of controversy across these two and disagreement across these two perspectives or philosophies are what we could call single world effects, just in the sense that they don't have this metaphysical cross-world quality, but that the interventionists would say do not reference sufficiently well-defined interventions. And canonical examples here, the effect of obesity is one that has been widely discussed and debated across many commentaries. You can find them in Epidemiology, Journal of Causal Inference over the last few decades, effect of marriage, other examples, effect of gender, effect of sex, and so on. And the interventionists would refer to these as, quote, ill-defined effects. So closely related to this disagreement, particularly on the acceptability of such ill-defined effects, are that the perspectives across these two philosophies notably differ on how to understand the so-called consistency condition in causal inference. And I don't mean consistency in the statistical sense, so we can call this causal consistency. And for those of you unfamiliar with this condition, I'll describe it in a minute. But basically, the non-interventionist views this condition as a definition or an axiom that's guaranteed under the investigator's counterfactual causal model. And again, someone coming from this perspective is talking usually about Pearl's NPSE-MIE model. While the interventionist argues that this is an assumption that specifically can be violated when there are, quote, multiple versions of treatment, which is often a problem ascribed to so-called ill-defined effects like the examples that I gave before. But both sides seem to agree in the meaning of consistency. And if you look at the literature, it is universally characterized as a condition that is needed to link counterfactual outcomes or counterfactual variables, which we would use under some counterfactual philosophy of causal inference to define causal effects, to link counterfactual outcomes, counterfactual variables, specifically to measured ones in the data that we have right now available that we're about to decide on how to analyze. However, if you actually look at the causal inference literature and all that is available in the causal inference literature, despite what has been communicated more popularly, these two philosophies or frameworks, whatever you want to call them, the non-interventionist one, a la the NPSE-MIE literature, Pearl's and NPSE-MIE model, or the interventionist one as communicated by the target trial emulation literature, these are not the only ways to formally think about reasoning from a causal question to a statistic or causal inference with real-world data, despite their pedagogic dominance. And there's a third option that I now call story-led causal inference, just because you need a nice, concise name for anyone to pay attention to what you're trying to say. So what's different about this third framework, or whatever we would call it? The key distinguishing features of this philosophy are that it accommodates and allows transparent thinking about causal effects of treatments that we didn't measure in the data set. And further, counterfactual targets under this way of thinking are first and foremost driven by subject matter stories told by the investigator rather than driven by the data that happens to be available for analysis. So under this approach, and I use all of these terms in quotes because they're very broad and could apply to many statistics and many data sets and many problems, the definition of consistency can also be understood much more broadly, rather than as just thinking as a condition to link observed to counterfactual variables, rather just a condition that would link factual variables to counterfactual ones. So we may not have measured all of these factual variables, but they certainly might be measured in a better study than the one we unfortunately were limited in right now, which is an important distinction. So, and I just want to take a moment to note that causal stories are important for all study designs with causal goals, not just observational studies, which is usually where these controversies about, quote, ill-defined effects are most prominent, like effects of obesity, because we didn't randomize obesity, and which is why we're sort of able to start talking about this and debating this in an observational study. But this concept actually turns out to be very important in actual trials as well, because the target question, the actual story motivating the investigator, cannot always be immediately gleaned by simply knowing the protocol of a trial that was conducted. Engagement with a causal model, meaning assumptions on causal structure, including assumptions about what we might refer to as causal mechanism, may be a necessary first step to think about the trial that would answer our question. So this is, I think, the biggest limitation of the target trial emulation literature, that we really cannot, we need to start with the causal question, and that does not equate to the protocol of a trial. We need the question, then we can know what the trial would be that we would run. And this becomes very important when we have sort of post-randomization, quote, complications, like competing events, like a lot of other complications, that we really need to engage more with causal reasoning to even know what trial would be, would answer our causal question. And in terms of observational studies, which is what we're going to focus on here, observational researchers, in my experience, I've been doing this for a long time, often do have a sufficiently well-defined interventionist question, in the sense of a question that could be answered in principle with a trial, motivating them, even if their initial statement of it is ill-defined. And this is particularly the case when what they would intervene on, when you pull out the actual story, the actual treatment is not something that just is sitting in the data set that we have available. So from a formal perspective, there is a foundation for this reasoning. And the two papers that have very much inspired a lot of this for me are two papers by Robbins and Richardson and Robbins that give a lot of contributions. But what I'm going to highlight here are alternative graphical tools to causal directed acyclic graphs that really aid in transparency about thinking about what our question is and reasoning down to a statistic. So I'll illustrate this a little bit. So to make some of this concrete and to really sort of think about what are the differences between these three approaches, I want to think about an example that was talked about in a paper led by Paloma Rojas Sanero in published in Epidemiology in 2024. And this was the commentary that I wrote, called Story-Led Causal Inference, used this example as a way to think about this third, whatever we call it, framework. And what they talked about here, they considered observational studies, many longitudinal cohort studies. They considered specifically the Rotterdam study, consistently reporting evidence for a purported protective effect of cancer on dementia, which is exactly the type of effect that the interventionist would qualify as ill-defined, and the non-interventionist would say this is fine to ask. So now we're going to introduce just a tiny bit of notation, but I'm going to explain all of it. So, and it should, you don't have to worry about it if it feels too much. So we're going to think about a setting where investigators, say, have data available to analyze on variables L, R, and Y, let's call them, where L just denotes a vector of the types of covariates that are typically available at the start of a longitudinal cohort study, like the Rotterdam study or other cohort studies, and these would typically be measured by a questionnaire. So things like demographics, reported health history, maybe reports of health behaviors, and other things I'm sure many of you have experience with cohort studies. We're going to call R an indicator of incident cancer by the end of a specified follow-up period, say, let's just for concreteness, say 20 years. And we're going to call Y an indicator of incident dementia by the end of that follow-up as well. So a quick disclaimer, this is a simplified version of the data structure in a longitudinal study like this, in the sense that this cancer and dementia process would be time varying processes where people could jump to, yes, have incident cancer at any arbitrary time and dementia at any arbitrary time, just to make the subsequent formulas that I show you very simple to digest. We're just going to consider a trivial version of this where if cancer occurs, it occurs only at some fixed interim time of that 20-year follow-up. For everyone, and if dementia occurs, it occurs at some later time, but there is nothing required. This is not a requirement to apply some of these ideas in practice, again, just so we can show much simpler formulas to digest some of the comparisons here. So basically, in this simple context, Rojas and Nera et al. Think about potential sources of bias in an analysis that is specifically set up to estimate this particular function of the measured variables, L, R, and Y. So this is just something we could go after with some statistic. I call this psi tilde R star equals 1. And this is what that function looks like. So this is a special case of Robin's G formula. And just, it doesn't, the details here do not matter, but too much. But just if you haven't seen a formula like this before, this is just the conditional probability of incident dementia in the study among those with a particular cancer status, 1 or 0, they got it or they didn't, and a particular joint level of those baseline covariates. And this is just standardized with respect to the distribution of those covariates. So again, this is just a function of the joint distribution of these measured variables, and it's a case of what in the causal inference literature we would classify as a case of a G formula. So there are a range of statistical methods available to estimate a difference in this function under the two possible levels of R, in this case incident cancer, 1 versus 0. And they differ only with respect to how they deal with the fact that L can take a lot of levels. For example, L could have a continuous variable in it. So IPW is one possibility, parametric G computation. There are sort of double or bust methods. ANLE is an example. Some of you may have heard of some of these methods. Some of you may have implemented them. The details of these methods are not what we're going to talk about. But the point is that all of these methods would be lumped under the umbrella term causal inference method. So why is that? Well, under particular assumptions, this difference in G formulas, again, on its own is just a function of the observed data, something we can estimate with one of those statistics, formally identifies, or that just means equals, an average treatment effect, which is defined as this particular difference in mean counterfactual outcomes, where Y R star equals 1 refers to an individual's, in this example, dementia status, incident dementia status, had possibly contrary to fact. We could think somehow ensured they had cancer status R star. So we're thinking about this for ensured they had cancer versus a case where everybody did not have cancer, because this mean refers to the entire study population. So that's what this counterfactual is formalizing. So what are the conditions we need for this equality? Well, if we could assume that this conditional exchangeability assumption holds, which would sometimes be referred to as no unmeasured confounding, conditional on the measured confounders L, with respect to this particular counterfactual outcome. So Y R star is independent of the actual cancer status someone had, conditional on levels of the measured L. And then here's that consistency condition we referenced before, that if someone actually had cancer status level R star, then we can equate their observed dementia status to that counterfactual one. And then finally, we have this positivity condition, which just says that there are people with both levels of cancer in the population, conditional on any level of L. So if we can make these three assumptions, then we can equate that difference in counterfactual outcomes to that observed data function we saw before. Now, due to the specific arguments that I just gave you, you might actually see this G formula specifically referenced as a G formula characterized or indexed by a deterministic intervention that sets R to R star for everyone in the population. But again, on its own, this is just an observed data function that we could estimate with statistics. So basically, Rojas and Arrow et al., their example described to this point has an identical setup to other examples of ill-defined effects, like the effect of obesity, that have been widely debated in published commentaries in journals between the interventionist and non-interventionist perspectives. And by setup, what I mean is that so far, let's think about what we know. We know that an investigator measured L, R, and Y. We know that they've suggested R is their treatment by maybe stating interest as with an effect of R on Y. And they're using some statistical method, or they're asking about using some statistical method, targeting a contrast in that particular G formula that we just talked about. So what would so let's think about how we would approach this particular problem from the non-interventionist perspective versus the interventionist perspective. And then let's think about how a story-led approach would differ. So the non-interventionist reaction to identical setups has been, well, as long as exchangeability and positivity hold, it's perfectly fine to use this analytic approach, as it will identify this effect that we just talked about. So any causal concern about this analysis would just be about violation of one of these two assumptions, conditional exchangeability or positivity, because from the perspective of the non-interventionist, consistency is not an assumption, but it's a definition that holds under the investigator's counterfactual causal model, which actually embeds these identifying assumptions, in particular conditional exchangeability, and again, which we could be implicitly at least represented by a causal DAG, which we could use to reason about that assumption. So let's make that part more concrete. So here's an example of a causal DAG. I don't know if everyone seen a causal DAG before, or some familiarity with this. So this is an example of a causal DAG implicitly aligned with that exchangeability condition. And I say implicitly because there's no counterfactuals shown on this DAG. But it's aligned with the condition that YR star implicitly is independent of R given L, because conditional on L, basically we block all backdoor paths between R and Y, or we could say the only remaining open paths conditional on L are causal, connecting Y and R. And this is because L is the only shared cause of, in this case, R and Y shown on the DAG. Now, for a causal DAG to correctly represent the investigator's causal model, which was a premise of the non-interventionist, a minimum requirement is that all common causes of the variables depicted on the DAG also be depicted. So when we think for 2 seconds about what L, R, and Y are, obviously this is not correct, because L are just things measured in a questionnaire maybe 20 years earlier. R is a very complicated process, as is Y. So clearly this is wrong. So let's make it a little more realistic and add an unmeasured common cause of R and Y. In that case, the conditional exchangeability that we said we needed would fail, and the non-interventionist would concede that, okay, well, yes, there's a problem with that original analysis, and it's because we have unmeasured confounding, because now the conditional exchangeability condition fails. Oh, sorry. My clicker's not working.
Further towards the table, because the computer's in the table.
Oh. So this is the non-interventionist conclusion. The problem is no unmeasured confounding. And this is going to drive their diagnosis of what should be done, how we could improve this in the future. They diagnose the problem as unmeasured confounding, so that suggests that the solution is to measure that variable u, but go back and repeat. If you did measure that variable u, you would repeat the same analysis that was originally posed for that same G formula defined by psi tilde R star, but just you would want to include the u's with the L's. You would want to adjust for them in addition to L in the same way. Other options might be, they might be able to think about some formal sensitivity analysis or bounds for that stated ATE defined by the R star interventions. under, say, this broader, more flexible causal model that allows for U. So, okay, what would the interventionist say? Well, the interventionist would, in contrast to the non-interventionist, say, no, consistency is an assumption, and it's violated here because there are multiple versions of treatment. And the argument would be there are multiple ways that one could ensure R takes the value R star, and these different ways could have different effects on dementia. So the diagnosis of the problem from the interventionist perspective is minimally framed as failure of consistency, and specifically failure of no multiple versions of treatment, with R the ostensible treatment. So what is their solution? Well, the only solution that you can find from this perspective discussed in the literature for the multiple versions of treatment problem is to reframe the causal question in terms of interventions on all the quote treatment versions. For example, instead of considering the counterfactual outcome Y R star, you could instead formalize your effect in terms of, say, Y K R star, where K is the vector of all the versions of the interventions R star. The problem ostensibly here is that this solution, when it's been posed, has been posed rather skeptically, quickly dismissed with the argument that, well, we may not know all of these versions, and further it would require adjustment then for more things, not only all the shared causes of R and Y, but also all the shared causes of these versions of R and Y. So ultimately, the suggestion is that the problem is consistency or multiple versions of treatment, but it's really not clear that there is a solution. And in fact, the practical impact of that is that investigators who are in this situation basically flock to the non-interventionist literature because you're given a solution there. You're able to do something at least. So how does a story-led approach differ? Well, this is almost silly, but under a story-led approach, the reaction should be, we are not going to attempt to diagnose the problem or pose a solution to it because the information that has been given is just simply not enough. All we know is the statistics that were implemented. We have no idea what this U means. We don't know what it is. And we have a purported target effect that, at least as stated in words, is unclear. I don't know what is meant when someone says an effect of obesity or an effect of cancer on dementia without more information. So under a story-led approach, an effect deemed ill-defined is understood simply as an effect, not where there's violations of multiple versions of treatment, but that it's just an effect that I don't know, I don't understand this, and I actually don't even know what the treatment really is. And so to advise on data analysis, we need a more detailed story from the investigator or the subject matter expert. So I usually end this talk with this, but this is often really what's burning in a lot of people's minds when we talk about this, especially when talking to biostatisticians who are not subject matter experts and work with folks and they don't know what the story is and they don't know how to draw it out. So this is a strategy that I have used that I actually have found is pretty successful. So basically you can think about removing all of the usual statistical thought process. Suppose I give you code, I guarantee you will get the right answer. If you run this code, your results will be in the direction you expect, statistically significant. How would you write your discussion at the end? So let's have this conversation before we decide on an analysis. Let's write the discussion if you find what you were expecting. And usually in discussion sections is where you really see what the story that was motivating things are. And a lot of times as we look through these, the discussion when this happens after the analysis is done does not align with what even exposure was called in the analysis or what treatment was called. And that is often going to be the case when we're dealing with so-called ill-defined effects, or at least this can be the case. And in fact, this is for another talk, but sometimes these stories are not even about causal effects. And it turns out this is not a causal inference problem. And we can think about this in terms of prediction or other things. So let's think through the story. So basically Rojas and Nero and I'll tell a detailed story. And Paloma is a subject matter expert. She's a medical doctor who has really delved into this literature. She's read a lot of discussion sections. She's spoken to dementia researchers and at least understands some what some people's motivation is in this type of setting. So they clarify that what actually motivates many investigators who are doing these studies of cancer and dementia, even using so-called causal inference methods, notably dementia researchers, the underlying story is about PIN1 gene expression, which how would we ever have guessed that if you're like me, know nothing about this topic? So I don't know anything about PIN1 beyond what's in their paper, so don't quiz me on the biology of PIN1. But apparently PIN1 is overexpressed in cancer tumors and underexpressed in the brains of dementia patients. And there's a hypothesis that PIN1 could be a common cause, a shared cause of developing cancer and also developing dementia. So Rojas and Nero et al. Clarify that such investigators who have this story in their mind really want to interpret associations between R and Y as support in some way for future development of drugs for targeting PIN1 as a candidate dementia treatment. Now, there's another complication in this story, of course, if we sort of think about, okay, but PIN1 is assumed to be a shared cause of cancer and dementia in opposite directions. There could be a side effect of these drugs that would increase cancer risk. And that's something we would have to think about. And I have some discussion of that in the commentary. This involves competing events, but we're not going to have time to go through that. So we'll sort of forget about that, that problematic potential mechanism of this drug, and just think about how to answer a question that would be more grounded in this story. So this clarifies that the question for such researchers is not about R-star counterfactual, forcing everyone to have cancer versus no one to have cancer. Rather, a correct formalization would reference a completely different counterfactual indexed by interventions on treatments that are unmeasured in existing data sets. Here, a PIN1 targeting drug. So, and I just want to qualify, I'm using unmeasured in two different ways here. So in this example, unmeasured really just means the drug doesn't exist. So in fact, we actually have the outcomes for people who don't receive this drug. Those are what everybody has now because nobody receives it because this drug doesn't exist. So in this case, the drug is unmeasured in the sense that the having the drug scenario is unmeasured because this drug is not developed. But I'm going to formalize the rest under the simpler assumption where there are people who receive it and don't in the real population, and just our study doesn't have a measure of this. But we could extend sort of this story-led thinking to the former case. And in fact, that case is a lot of what motivated this, this name, story-led causal inference. And it's born out of this literature on so-called separable effects, which was posing ways to reason about how to identify effects of future, currently non-existent treatments given mechanistic connections to a different existing measured study treatment. So this work is led by a few authors, including Vanessa. And there's a really nice new paper that I just wanted to give a shout out that gives a really nice, very recent, very story-led application of this idea. That's just on arXiv, but it's a nice example. So let's now think about this story a little more in more formality. So this is the exact same causal DAG that we showed before, allowing an unmeasured common cause of cancer and dementia when we just sort of loosely called it a U and the non-interventionist diagnosed the problem as unmeasured confounding. But now one of this U could be PIN1. This matches the story that we were talking about before, but PIN1 is not an unmeasured confounder because now we're clear that R is not the treatment. So PIN1 is something that would be affected by the ostensible treatment, which is not even shown here. So we could think about causal diagrams that really more explicitly show our story, not just engage with the variables that we have measured and perhaps loosely some unmeasured confounder. So on the left, we have a causal DAG that explicitly depicts the actual treatment, which we'll call Z. And it also depicts an assumption that Z works as desired mechanistically, meaning that this would only affect pin 1 and it would not affect the other variables on the graph via other mechanisms. Now, we don't have to make that assumption, but we're making it here as just an illustration of how that would implicate things. And on the right, we have what Richardson and Robbins called a single world intervention graph, which is a node splitting transformation of the DAG that explicitly shows the counterfactual outcomes, where the nodes that are split are the intervention nodes. So now we can clearly see that the node that would be split is not R, and we would not think about an intervention that determines R 100%, but rather this intervention Z. So the counterfactuals are indexed by Z, and in fact, here we can see that R under the intervention Z, and we maintain it as capitalized because it would still have a distribution under Z. It would not be 1 for everyone under some Z, or not 0 for everyone under another Z. It would be stochastic in this sense. So by understanding the SWIG as a Z-specific, intervention-specific transformation of the causal DAG, we are inherently making a consistency assumption to go from the left to the right, which allows us to link factual variables to counterfactual ones, specifically these Z-index ones. But we can see that this is a very different consistency assumption that was originally debated. It does not reference an R-star intervention, and it does not an assumption that only links observed variables to counterfactual ones, but more generally factual ones to counterfactual ones, because Z and A in this case are not measured or observed in the existing study. So now we actually have enough information to define an effect that would be the investigator's target. It would be an average treatment effect, but of Z equals 1 versus Z equals 0 and Y, not R star. And in this particular simple example that I've shown you, based on the SWIG that I showed, or the DAG that I showed, it turns out we could identify it in terms of this very simplistic factual data function. And to understand that, we can see that Z and Y share no common causes in this example. So this is assuming a simple case where there's actually marginal exchangeability for this counterfactual outcome, that Z is independent of YZ, conditional on nothing, but we could obviously extend this to allow assumption that there are confounders in that case. And so provided that we have positivity that there are people with Z equals 1 and Z equals 0, and this is this simple case where Z exists, there are people who have the drug, and we're just assuming we don't have a column in our data set knowing that, this should hold. But this is a factual and not observed data function because Z is unmeasured. So it's very simple, but we still have a problem because we don't have Z. So now we have a very different diagnosis of the problem with the original analysis that was posed. The problem is that constructing any even wonderful statistic for a difference in this, for R star equals 1 versus R star equals 0, does not equal this for Z equals 1 versus Z equals 0. And we could show that these are not the same. This is the thing that we want to target with our analysis in some way. So now we can actually think correctly about what long-term solutions are. It's not to measure this confounder and then conduct the original analysis with that as a confounder. We have a clear understanding of what anywhere from long to short to very short-term solutions might be that would be better than what we started out with. So obviously, the best thing we could do is go out and measure Z, maybe even randomize it, and then we would have the target trial. This would be the trial that would answer our causal question, and that before factual data function would become observed, and this is about as you could use as simple statistics as you can imagine to estimate this. Nothing fancy, but it's still causal inference methods because this is a causal question, and we've reasoned to it through a very clear reasoning process. But this may be a very long-term solution, of course, if Z is not yet developed, and we want some observational evidence to maybe inform whether this is worth doing. That's part of what's motivating these researchers in the first place from the story. So what are some shorter term solutions? And this is kind of what Paloma, Rojas and et al. Were suggesting in their paper. We could conduct an observational study that actually measures PIN1, and how could we leverage that to go after this? So first thing, we can note, at least under the example that we showed, because of that mechanistic assumption that the only arrow out of Z goes into A, we can rewrite our actual target in terms of just this other form. So these would be equal, but only under that mechanistic assumption. And what's important to note here is that all the terms of this new way of writing the target do not depend on Z. The only one that does is this term. So in an observational study where we now, instead of just L, R, and Y, we also measured A, this would be something we could go after with statistics, barring this one term. But it turns out that this functional, which is not quite an observed data functional, even in that next study that measures A, but pretty close, turns out to coincide with another G formula indexed by a stochastic intervention on A. So there is a literature on statistics for a G formula of this form, where this term would represent an intervention distribution on A. And under the assumptions of our SWIG, in that study, this term would equal the distribution of A had Z been implemented, conditional on L. So now the remaining challenge in this now not perfect study, not the target trial, but a better observational study, could be to take a guess at, or a range of guesses on what this distribution would be under Z. And so what would be some ways to think about structuring that guess? Well, given that Z is defined as an indicator of receiving a drug that would target increasing PIN1, one candidate for this intervention distribution could be a shifted version of the observed distribution of PIN1, which we could estimate from the data in that observational study, conditional on L, based on various positive shifts, which would give some range of estimates for what we might see under this intervention. And there's a whole literature on statistical methods for estimating a G formula indexed by a stochastic treatment intervention that depends on the observed treatment process. So this is a whole literature that has been something I've thought about too for a while. There's a range of estimators, TMLE, IPW, G computation. But another thing to keep in mind is this is a squarely interventionist motivation for this type of statistics that would not be obvious without this story, even in this new study, because the interventionist would also not like thinking about a stochastic intervention that somehow draws a random number and assigns you a value of PIN1. You can't do that either. But that's not what this story is about either. We're motivating this from an interventionist story, but we might leverage methods that are not immediately obvious without that story. We could even think about a shorter term solution where we just do the best we can with the data we have. We don't have A, we don't have Z. All we have is L, R, and Y. So let's think about another instance of a stochastic G formula, which I'm going to call psi tilde Z. So remember before we had psi tilde R star? This is actually the same as that, except now I have this extra term, which we can think of as an intervention distribution on R under the intervention Z. So we could similarly take a guess at that. And the point is, this even under our SWIG, any perfect estimator of this is going to be biased for psi Z because we're going to need more assumptions for them to be equal. But what I just want to draw your attention to is that if we think of this as a guess, if we were to estimate this under a guess at the distribution of R under the intervention Z, it would not be what we could call a degenerate distribution at R star. It would not be 1 at R star and 0 otherwise, which is what it would have to be for that first naive G formula to make any sense for this problem. So from that perspective, this is still more aligned with the question because it's allowing that cancer would have a distribution under this intervention that we're thinking about. And because of the hypothesis that cancer incidence would be increased, we could again think about shifting observed relative to now under Z, it could increase the chance of cancer conditional on L. And that could be specified again with these sorts of stochastic G formula methods that specify shifted observed distributions, just as an example. So the bottom line, however we choose to proceed, we're still better off having led with a story over data. We can now correctly diagnose bias sources, and this or any analytic approach, this meaning the original one posed based on the R star G formula, because we actually understand what the target is, and we can think about an approach to best approximate or give up and think about a new story, but we can do that in a directed way. Even our worst option in this case is arguably a better option than the naive one that we started with without any understanding of what the question is. So that's actually all I have to say. Thank you.
Thank you very much. That was very interesting and thought-provoking.